me to I haven't actually used this before in class. I've used markdown editors before and renderers before, but this is the first time I've used this one, which has all of the features that I've finally been looking for. But it still is untested. As I type, you should see updates every half second or so. And if you don't, then just go ahead and shout out that I need to save the file so that you do see those edits up there. I wanted to basically go on the coattails of what you did yesterday in lab and take you through the process that you went through in a little bit more detail before we actually get started on the anatomy of a program. For that, I'm going to take the same Hello World program that we used on Monday and the one that you used on Tuesday, and I'm going to go through that compile and run process, but I'm going to go through it in much greater detail. As you saw, a program starts out as source code. In general, source files are simply just plain text files, right? Containing computer code. Right? So it's not a Word file. Do not use Word or some other rich text document editor to start coding stuff out. You do need a plain text editor. That's why I recommend Atom.io. If you want to go ahead and learn Emacs or VI or something like that at the command line, that's up to you. I'm using Atom.io right now to do this lecture. It's free, open source, and very nice text editor with lots of code and syntax highlighting. Yeah?
So we were just discussing, like, how would you use it in order to compile one of the, like, the Hello World?
Good question. It is just a text editor. What you're looking for is what's called an IDE, an integrated development environment, where you've got the text editor, the terminal, and your compiler all built into one program. Something like code blocks would be appropriate there if you want to go that route. And Eclipse is also another one that comes with stuff. I wouldn't worry about that. I would just connect to the CSE command line and use their GCC compiler, so you don't have to install a lot of stuff. Especially later on, there's going to be special libraries that are only available on CSE. And if you're doing your own development on your own machine with your own compiler, then you're going to run into some problems. But you can go as a little hobby. I encourage you to go ahead and go off and try that. But always have something like this as a backup here. All right? So once we write our code in a plain text file, source files are then assembled into what's called assembly code. And then assembly code is then actually compiled into machine code. And I'll come back and explain both of these here in a second, and I'll give you a nice visualization of it. But basically, it goes from source. Right? Let's see how this looks in the render. It goes from the source to the assembly to the machine code. That's the basic process. The way that you did it is yesterday in lab, when you ran GCC, you started at the source code, and then that one command took you through that entire process. In fact, there are even little tiny little processes along the way here. I'm simplifying it. There's also something called a linker. And there's the compiler actually goes through code optimization. So there are dozens of other steps along the way. I only want to look at these 3 steps right here. If you're interested in those little tiny steps, you're looking at a complete course by itself, a compiler course, a programming language course. You're probably looking at several courses there. I want to look at a high-level view of what's going on here, and so I'm simplifying it to these 3 steps only. All right? You can see the kind of a hierarchy here, though. When you start out with that source code, it's not exactly English, right? Let me go ahead and go display that Hello World program so that we can look at it. All right? There's that Hello World program again. Now, it's not exactly English, but at least it's readable by a human being. You can look at it and say, well, you're including something. I don't know what exactly that is, that .h file there. You've got a main function. You've got these arcane keywords, int, char, and a bunch of other things. Printf, that kind of tells me in plain English that it's going to print something. And then I do have some plain old English in these two double quotes, right? That's called a string, right? And then I've got a return statement here. I'm using English words or English abbreviations to dictate to a computer what to do. Now, a computer does not, so it's not exactly English, it's one step below English. But it's still not something that a computer can understand. We need to go through this hierarchy here of taking something high level and making it lower and lower and lower level until a processor can actually understand and execute those commands. Yeah, question? Or, no? No? Okay. All right, yeah, question.
Are a lot of commands similar to like Python? Like, for example, in Python, if you wrote int, it'd be like integer?
Yeah, but Python's dynamically typed, so you don't have an int in Python, do you?
Well, no, but like, for example, like how the different words are highlighted different colors, like those kinds of
Correct. Those are reserved words or keywords that the language itself are defined in the language itself. Right. Now, some of the I do have two variables here, int or argc and argv. Those are variable names. In something like Python, you don't have variable types, which is something we'll talk about later on today. Here, like int and char, those are the types of variables. You have to assign them a type, and you have to declare them before you actually use them. Python is dynamic. You don't have to do that. Right? Although that comes with its own pitfalls. Don't think that that's the best way of doing it. Right? So what I want to do is I want to, again, go through this hierarchy here of taking this high-level source code and translating it into assembly, and then translating it into machine code to see how we're taking something abstract and making it less and less like English and more like something that a machine can actually understand. So to do that, I'm going to go through a demonstration here. Again, typically what you do is that you edit a source file, hello.c, and that's what I've done on the command line here. Then what I'm going to do is I'm going to assemble it. And to do that, I can use GCC. GCC does everything. It optimizes, it links, it assembles, it compiles. To do this, I'm going to use a special flag called -S. All right? Now let me go ahead and go back to my command line here. GCC-S hello.c. All right? Remember, no news is good news. That means it's successfully assembled. All right? So what did it actually do? There's this brand new file in here called hello.s. Let's use that same utility that I was using on Monday to ask the operating system, what is this file? In fact, let's do it on that hello.c file first of all. It says that it's a C program, right? It's smart enough, ASCII text. We'll talk about ASCII later on. It's just a plain source file with plain text, and it happens to interpret that as, well, it looks like a valid C program, right? Let's ask the same question. What kind of file is hello.s? It's assembler source text. Okay? It's actually assembly code. It's not what we originally wrote before. What we originally wrote before looks like this. Right? And sorry about the noise. Let's go ahead and go with mute on the program audio. All right, there we go. Hopefully that doesn't do that again. But there's the original. Now let's go ahead and look at what the assembly code looks like. I'll go ahead and open it up in a text editor called Emacs. Right? Looks a lot less like English. But it still has some things that are legible, some things that are readable. For example, MOVQ. Move Q, that's short for move Q. LEA subQ, maybe that's a subtraction protocol. That hello world text that I embedded in my program, that must be in here somewhere. And indeed, it is right there. Right? So it took that plain old text that I wanted to print out and actually embedded it into my assembly code. But this is not something that is easily readable. Imagine if you had to write programs in assembly. Right? That's how it used to be done before high-level programming languages like C. In fact, how it was done before even that, was you actually wrote in binary. You had punch cards. This is the 1940s, 50s, whatever, where they actually punched out little dots to indicate a 0 or a 1. That's how they actually programmed. So in other words, they were taking high-level ideas and writing it down on paper and then translating it into binary, all manually. Right? It was all a manual task. This, at least, was a little bit of a step above that. You could actually make commands like take the value in register 1 and take the value in register 2. Registers are things on processors where things are stored. And then add them together and store the result into register 3 so that I can see what the addition of those two numbers is. Right? That's basically what assembly code is. Now what I'm going to do is I'm going to take the next step. I'm going to go from assembly to machine code. And to do that, what I'm going to do is I'm going to compile. All right? So I'll compile without linking. I'm going to go use GCC again, but I'm going to use the flag C, hello.c. Now, the flag S, it's kind of stands for assembly, but not. The flag C here actually does make sense. It stands for compile. All right? So let me go ahead and go back to my command line here. GCC-C hello.c. Again, no news is good news in the Unix-Linux world. Let me go ahead and clear this out so that we can take a look at it. What that did is that produced a hello.o file. Let's again ask the same question of file. What type of file is that? It's a Mach 0 64-bit object. It's an object file. What happens when you compile is you compile it into a bunch of machine code. I briefly displayed that on Monday. It was a bunch of garbage to us. And in fact, today, it is still garbage to us. If I were to open up this file in Emacs, it'll probably even give me a warning. Nope, it doesn't. And it's just a bunch of garbage. Right? It's a garbage to us. It's not garbage to the machine. The machine can actually look at this and run it and execute those commands that it would it's all binary. It would interpret it as binary commands. In fact, if I try to more this, it'll probably give me a warning. It's a binary file. Do you really want to see it? Right? Because it's not going to make sense. Right? There are better ways of making sense of binary files. You can use a utility called hexdump, hello.o, and it'll format it. It's still not readable or anything like that, but at least it'll format it in a nicely legible format. This is hexadecimal, base 16. Usually we think of base 10 because we've got 10 fingers and toes, right? Well, computers don't think like that. Computers think in 2s, 0 and 1. That's what binary is. That's not the only base system. You can have octal, where you have only 8 numbers, 0 through 7, and then you start repeating. You can have decimal, 0 through 9, and then you carry over and start repeating. Or you can have base 16, you can have base 64, you can have whatever base you want to come up with. Various bases are used in computer science. At its core, though, everything is binary. And the reason everything is binary is because that's much easier to store in a computer, especially those electrical engineers out there. Think about having to distinguish between, say 10 different amplitudes. A low amplitude, not so low amplitude, another amplitude, megahertz, whatever, however you want to measure it. You would have, first of all, there's a huge run-up when you go from a low voltage to a high voltage. If you have to go all the way up here to be able to distinguish these 10 different categories, then you're talking about a lot of time. To get up there. A lot of time as in nanoseconds. Nanoseconds turn into tens of nanoseconds. And now suddenly all your electronics are extremely slow. Not only that, but they're also prone to error. Binary takes care of all that by only having 2 frequencies, low voltage, high voltage, low frequency, high frequency, pit or no pit. Right? There I'm talking about storage mediums like CDs. How is data actually stored on a CD? Well, there are these microscopic little pits or rivets. And the absence of a pit means that it's 1. The existence of a pit means that it's 0. Imagine if you had to distinguish between 10 different types of pits. Right? Now when you scratch a CD, it's probably going to be unrecoverable. Right? So in computer science, we always go with binary, and that's what binary looks like when at the end of the day when you actually execute it. There's another, but what you did yesterday is what you should probably do. If you don't want to go through this process every single time of starting with a source code, moving on, then assembling it into assembly code, then compiling it and linking it into some executable. That's why if you just run GCC up front with hello.c, then it does that entire process in one shot, producing, typically, an executable file called a.out. Now, you can rename that, and you probably explored those types of commands in a lab where you specify a different output file. But again, let's go ahead and ask what type of file is that? It's an executable file. It's not just an object file. You can actually run this program. And so when you run this program, you see the results that we had yesterday. And it printed on one line here. I didn't put in my end line character. We'll discuss how to do that later. All right? But that's the process in a nutshell. Again, you'll want to go through that entire process with just one command. Yeah? Sorry? Linking? Okay, a good question. We'll get to that later in detail, but basically, here's your program, right? In fact, let's go back to the Hello World program here. More hello.c, Emacs, hello.c. There's your program, right? What is printf? It's a special function that exists in a library over here that takes whatever you give it and prints it out to the screen. We didn't write code here to specify, well, now you need to print the letter H, and it's this pixel, and this pixel, and this pixel, and that pixel, right? We didn't write the code to then go to the next line or anything like that. Instead, it was in an external library. That very topmost library, stdio. IO stands for input-output. So the idea of linking is we've got your program over here, but you're using this library over here. So what the compiler does is say, OK, I'm going to compile your program. Oh, it uses code that's stored over in that library over here. I will link it in so that I can bring these two things together to actually build a program for you. Right? And you'll be doing that process directly when you start writing your own libraries. When you start writing modules and header files and your own functions that you store over here, and then the main program is over here, you need to bring them together. That process is called linking in. Right? All right. All right, so again, all in one shot is going to be gcc hello.c. Let me go ahead and copy that over. There we go. All right, so program basics. I just wanted to make sure, I just wanted to show that to you as a demonstration so that you have a high-level view of what we're actually doing here. And so that it demystifies it a little bit. It's no longer magic. I just type this command and it builds this program. No, there's a lot going on behind the scenes there. All right? Here is, sorry, let me go ahead and go over here. Here is a nice little program. Let me go ahead and change that date. What is today? 22nd, so August 22nd, 2018. There we go. All right. So here's a nice little program. We don't know any C just yet, but we can probably look at this program and start dissecting it and getting an idea of what it might be doing. So I've got those same includes up there, and as I alluded to, those are bringing in external libraries. The standard input-output library and the stdlib library, that's just the standard library. That holds the core of the C library. Then I've got this hash define KMS per mile. And I set it to 1.60934. What do you think that is? Or what do you think the purpose is? It's defining how many kilometers are in a mile, right? So already I have a hint as to what this program does. But if I started up above that, I would not have to have a hint as to what this program does. What does it say up there? This program converts miles to kilometers, right? That up there is what is called a comment. It's documentation. And this particular documentation, or this particular comment, is an advertisement to other developers, other programmers, of what the purpose of this program is. So that I don't have to go down and start reading line by line. OK, what does this program do? What does this function do? I have to read every single line of it to understand it. No, I can just read the plain English at the top there, right? Wouldn't it be great if we could just simply program like that comment? Make me a program to convert miles to kilometers. Again, we're not there yet. That's Star Trek level stuff and natural language programming. In fact, that's why we have so many programming languages, because nobody can agree on what the best features or of a programming language, or what the best type of programming language is, or how to build a language, right? It's the same reason we have many languages, right? Everybody has a different opinion. There's no perfect programming language. If there were, then we would have it. In fact, the perfect programming language is natural language. When we build a computer to have perfect natural language comprehension, and we can tell it exactly what we want with no ambiguity or anything, then we'll have perfection in our computers. But until then, we still have to write code like this. Right? On that next line, I've got the main, which is the main entry point to a program. Any executable program is going to have a main function, and that's what it is. Don't worry about the rest of that stuff in the line just yet. We've got a long way to go before we get to understanding it all, but you can basically see that there's an opening a curly bracket and a closing curly bracket. Inside those brackets, that's where my program exists. Everything that I put inside those brackets is an executable statement that will be read top to bottom, left to right, just like we do in English, right? Again, high-level programming languages like this were intended to be as close to English as possible without actually getting there. And so you'll find a lot of similarities to natural language, to English. You've got the fact that it reads sequentially. It'll start at the top and read top to bottom, left to right. You've got certain punctuation. One punctuation would be what? On that next line, where I have double, miles, KMS. What's between them? A comma. In English, where do we use commas? In a list, and that is a list. I'm declaring two variables there. To separate them, I've got a comma. Right? I've also got ending punctuation. When you write a sentence in an English paper or in a paragraph, how do you know when the sentence is done? With a period. We use a semicolon here in C, right? to indicate that this executable statement is done. Right? I've got another comment there. That's a single line comment. And we'll talk about the differences here in a moment. But it's basically another message to the developer of what the purpose of this next line is. Now, I'm just using this to demonstrate the basics of a C program, not necessarily that you should have in fact, this is a bad comment in general. You shouldn't comment every single line in a program. A program should be self-explanatory. Anybody who has, say, had a semester or 2 years or 3 years of C will be able to look at the next line and know what it's doing, that it's printing out the message, please enter miles to the user. Right? I'm just doing I just put that comment here so that you can see an example of a comment. So it prompts the user for input, then it reads the input. So we've got a new keyword here, or it's not actually not a keyword, but it's a standard function called scanf. What do you think that does? It scans the input, right? And it places, and there's lots of other punctuation here, this ampersand, right? In English, we use the ampersand for and. It's not the same thing here. It's actually a referencing operator that we'll get to much later on. And then I've got KMS, so I read it into miles. So I prompt the user, please enter miles. Say they enter 25. 25 is now stored in a variable called miles. You're well familiar with variables, A, B, C, all right, X, Y, and Z. Anytime that you're doing algebra, you typically name your variables. Now, in pure mathematics, those variables may not have necessarily a connection to an actual value. You just use A, B, and C for coefficients. You use X or Y and Z for generic variables. Or you could use Greek, sigma, chi, et cetera, right? In programming, though, our variables are there to stand for something and to model something. In this case, miles is a variable that represents the number of miles that we're talking about. So we don't use bad variable names like from mathematics A, B, C, X, Y, Z. We call our variables what they model. I've got here KMS, which is short for kilometers, and I've got miles. Right? I read in the miles from the user, and then I go KMS per mile, which is 1.60 blah, 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 and then star, or asterisk. What do you think that is? That's multiplication. The reason that we use an asterisk for multiplication is because, look at your keyboard. Do you see times there anywhere? Nope. The QWERTY keyboard predates computing by many years. The QWERTY keyboard was set out, does anybody know what year? Any trivia? I don't know what year, but a long time ago. A typical typewriter was not meant to be an adding machine like a calculator is. So, so we don't have that multiplication symbol, either multiplication or just a dot or anything like that. We don't have that on the standard keyboard. So we need to use something else on the standard keyboard, and that thing is going to be the asterisk because it kind of looks like it, right? We don't want to use X because X is a letter, and we don't want to get confused because maybe we do want to use X as a variable name at some point, right? And so then we also have an equals here, right? If this were algebra, you would interpret that as an equation. This thing on the left-hand side is equal to this thing on the right-hand side. That's not how it works in programming. What it means is take the thing on the right-hand side, evaluate it. In other words, multiply that 25 miles that they entered by 1.60934. Whatever that, I can't do that in my head. You're lucky if you can, but whatever value that is, place that into the variable on the left-hand side. So in other words, at this point in the program, KMS now holds the value for however many kilometers is equal to 25 miles, right, according to that equation. And then we've got another print statement. %F, I don't know what that is just yet, but we'll get to it. Miles is equal to %F kilometers. And then I've got yet another list that I'm putting in, comma, comma, comma. Basically, I'm printing out to the user that 25 miles is equal to whatever 25 times 1.6 kilometers is. Then I also have some special characters. I have some special characters here. I've got the %F. That stands for floating point number. In other words, print me a decimal number. I've got, what is that? So there's a slash there. Is that a backslash or a forward slash? Backslash. How do you know the difference? Stand, right? And am I leaning backwards? Then it's a backslash. Am I leaning forwards? Then it's a forward slash. So that is a backslash. Backslash n is a special character that goes to the next line. I need that special character because if I simply just push enter or return or whatever to go to the next line, that'll actually affect my source code, and I don't want that to happen. How do I refer to special character? If I hit tab, that tabs over in my editor, and I don't want that. I want the actual special character to be printed, and so I use a backslash to escape those characters. Okay. All right. So we looked at our first program here. Again, let's go ahead and look at each piece independently. So comments are human readable messages embedded in code. Right? So you have single line comments. All right, good, it is working. They start with a, again, what is this? What are those things? Forward slashes, because if you stand here and you lean forward, that's a forward slash. So they begin with a forward slash, two of them. Right? So 2 forward slashes. And anything after which is ignored by the program and compiler. Right? All the way to the end of the line. Right? So whatever you put between your forward slash, all the way to the end of the line is completely ignored. It has no bearing. If you have 1,000 lines of comments in your program, it doesn't affect what the resulting program that actually gets compiled. In general, more comments are better. They're not going to slow your program down or make it inefficient or anything. Comments are there to communicate to other people and, by the way, to yourself. When you write a program and then you come back, say, a week later, 2 weeks later, a year later, right? Are you going to remember exactly what you were thinking on that day when you wrote that material? No. Those are going to be notes to yourself of what you were thinking, why you did something the way that you did. Right? And so you should put in that documentation. Multi-line comments begin with a /* and end with a */. Right? I had a multi-line comment up here, didn't I? this documentation up here. Sometimes we call this a header. Unfortunately, there's something else that's called a header in C, and so I hesitate to call it that, but that's basically what it is, right? Your program should at least have that in your first assignment, in your first couple of hacks. It's like writing an English paper. When you write an English paper, what's at the top? The title, right? But your do they not do this anymore? Name, course, and then over here, date, title, or you're putting in a header, exactly. And there's our header of a program. Yeah.
Why the extra asterisks?
Good question. Those are Java. Those are doc-style comments, and it just gives you a nice visual cue of a nice vertical line, and indicating that the entire thing is a comment. It's just a style thing, but also there are lots of doc style. If you write documentation in doc style, there are lots of tools that can then go through and then generate documentation in other formats. For example, Java doc style comments. It all comes from Java, and if you write in those comments, then you can just run this program. It goes through, pulls all those comments out, and then reformats that in HTML so that all of your documentation is online automatically. You don't have to adopt doc-style comments for this course. You're certainly welcome to, as long as you're being consistent about it. And we'll talk about style later on. Right? All right. But at the end of the day, for our purposes, again, it is just a nice visual cue that this entire block here is a comment. Of course, that the text highlighting here, the syntax highlighting, is also giving me that visual cue. It's all grayed out and it's all in italics, right? Doc-style comments predate that kind of syntax highlighting technology. But you can also get into ASCII. It's inspired by ASCII art, right? Drawing pictures with just plain old text. All right. So multi-line comments begin with a /* and end with a */. And everything in between is ignored by the program / compiler. Right? So again, the purpose of comments should tell the why and the how, not the what. Right? It's a note to yourself and to other developers. This is why I did this. This is how I did this, right? But the what should not be in there. Again, you should not. I did this for demonstration purposes up here of documenting more lines than I should have. Your documentation shouldn't do that. Your code should be self-documenting, right? I.e., code should be self-documenting, right? Meaning that any reasonably knowledgeable person can easily all right, sure, let's go ahead and grok what your code does. There we go. So what is grok? That's a bit of jargon, right? A bit of hacker jargon. Grok means simply to understand fully. It comes from, anybody know? Oh, no? Nobody reads old science fiction? It comes from Robert Heinlein's The Stranger in a Strange Land. And it was there are Martian characters and Earthling characters, and the Martian language had this word grok, and it was used all over the book. And grok simply just meant to understand fully, right? Without really, learning. You just look at something and you see it, right? So grok in this case means to understand. It's slang, right? All right. Comments should tell you the why and the how. Right? Why did you do this? Or I've got this nice little interesting algorithm over here that computes square roots using a Taylor series or something like that. That's excellent to document. You could put in a link to a scientific paper that describes the algorithm in full. You could put in a link to a Wikipedia page that describes a Taylor series or something like that from mathematics. If you use something complex like that, it should be documented. And it should be documented in the comments. It's a complex algorithm. Here is a high-level description of that algorithm. It should tell you that's the how and the why. It shouldn't tell you the what. This line adds A to B, right? Or like I did up here, this line prompts the user for input. That's the what. That shouldn't be in there. Read in the input. That's the what. That shouldn't be in there. If I took these two comments out, anybody with a sufficient amount of C experience could look at those two lines of code and see printf, yeah, I know what that does. It prints a message. So obviously they're prompting the user for input. Scanf, I know what that does. It reads the input. Right? Those things should not be documented because the code should be nice and clean and self-documenting. Anybody who knows C knows what that stuff does. Okay? All right. Also above were preprocessor directives. Right? So we're getting into the anatomy of the program here. These are directives to the compiler. Technically, there is a preprocessor, something that goes through the entire code before it's handed off to the assembler and changes the code. For example, one thing that a preprocessor could do is strip out all the comments because theirs aren't going to end up in the assembly code. And it'll go through, take all the comments and throw them out, and then whatever is left, then it goes on to the assembler. In this case, though, we were using preprocessor directives to define things. These are directives to the compiler that are executed before it starts compiling. Two of them brings in outside external libraries. Right? Yeah, that's right. That's right. Forget about any misspellings I have. Hopefully you can forgive me for any misspellings I have. But library, software is not built in a vacuum, right? If you had to start from scratch for every single machine, you'd have to write the assembly code or machine code to display the capital letter H. And you'd have to write the code that actually displayed this pixel, made sure that this pixel was white because it's not part of the letter, make sure that this pixel is black because it is, right? You're not going to do that. You don't reinvent the wheel. Instead, you use standard libraries to provide basic functionality. We didn't have to write our own functions to print to the screen or read from the input. Instead, those are provided in the standard input-output library. Later on, you don't have to write your own math functions. Sine, cosine, square root, tangent, all that stuff, that's in the standard math library. Where would you even begin to write a sine function or sine functionality? Well, what you would do is you would maybe do it with a Taylor series approximation or something like that, or some numerical interpolation method. You're going to be writing dozens of lines of code just to compute the sine. Well, that's such a common operation. Guess what? Somebody took and wrote code, and because they want other people to use it, they took that and put it into a standard library. And now nobody has to rewrite the sine function every time they need to compute the sine of some value, right? Eventually, later on, you will start creating your own libraries. I need this functionality, but it's not in any of the standard libraries, so I'll write it, and maybe I'll put it in my library over here, and then I'll use that as a function to solve an even bigger problem. Again, it goes to problem solving. You take a large problem, you break it down into smaller and smaller pieces until you can directly solve it, or there's an off-the-shelf solution sitting in the standard library for you. The way that you do that is through a preprocessor directive to include the library in your program. Yeah? Yes, like the stdio and stdlib, those, it's not C without those libraries. They're stored somewhere. They're precompiled object files sitting somewhere on the CSE server. I've never bothered to go dig down where they are, but you could. You could just go through. I'm sure that you'll have to go through several symbolic links to actually get to the actual binary code, but you could do it. Yeah. All right. There was another preprocessor directive up there, right? What was it? Define. That's called a macro. So define is a macro. So anybody have any extensive Excel experience? Yeah, what's a macro? Customization. I'll take just that word, right? In Excel, you can define a macro that you can actually record yourself doing this. If you've got a common operation in Excel, which is a spreadsheet program, you can highlight this over here and put that value over here and then do something over here and put that over there. You can record yourself doing that and store it in a macro so that next time you want to do that common operation, you just push this button and it runs the macro for you, right? It's an automated process. A macro here is basically the same thing. In this case, it is a cut and paste. In our case, it is a cut and paste directive. Right? In other words, all instances of, what was it, KMS per mile will be replaced with, what was it, 1.60934? Right? It literally, that's all the preprocessor is doing, is it's going through our program and taking any instance of KMS per mile, which there's only one in this case, and it's taking it and it's doing a cut and replace. It's cutting out KMS per mile and it's putting in 1.60934. Right? Why would we do that? Yeah. It's a little bit different. It's a preprocessor directive, so no variable actually ever exists. A variable is something that you can vary, right? That you can set and reset. This is not something that you can reset. You'd actually have to go back and re-edit the code in order to get a different value. If I assume that that's pretty accurate, but if you wanted it to make it more accurate and add more digits, then you'd have to recompile it if you did that. Yeah?
We want to do this because it's a lot easier than having to type the same number.
Exactly. That's one advantage, and I'll repeat that here in a second. A question? No? Yeah, way back there? It's never going to change, right? And if I just gave you the number if I didn't have this program here, and I just gave you the number 1.60934, without the context that we're converting miles to kilometers, would you have any idea what that number stood for? Probably not, unless you had, for some reason, memorized all those conversion tables. So what we've done here we've defined a macro for two reasons. One is to make it more readable. KMS per mile, that's English. I understand what that is, right? I don't have to just look at that, what we call them magic numbers. 1.60, what the hell is that? I do understand what KMS per mile is, though. And the second advantage here is if I use it in multiple places, this is a small program, so I'm only using it once, but if I'm using it in 50 different places, then I don't have to cut and paste myself the value 1.60934. Because if I ever did want to come back and make it more accurate, guess what? If I'm using it in 50 places, I've got to make sure that I'm consistently changing it in 50 places. Or I can change it in one place. One great use case of this is mathematical constants. There is a mathematical constant, m underscore pi, that represents pi, 3.14159, blah, 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 blah. Right? We all have one definition of pi, and so it's been defined as a macro. And you don't have to write 3.14 one place, 3.141 in a different place, and maybe a less 3 in another place if you want to get really inaccurate, right? Another question? Or, yeah?
You said it can't be changed later, including like if you were to just next line, it's pound defined there.
Nope. The preprocessor will fail. Like, what are you talking about? All right? That's not a variable. And we'll look at examples of the compiler choking on stuff like that. Another question? Good questions. Despite the fact that it's a huge section, we're getting some dialogue going. Good. All right. So again, the reasons are that it provides a single point to define constants, right? So that Any changes are reflected in all instances in which you use it. Maybe there's a less verbose way of putting that. And the second reason 2, there we go, 2. Let's go with reason 1 and reason 2. Right? And reason 2 is it gives you a more human readable representation. In general, avoid what are called magic numbers. Magic numbers are just simply numbers that are there and you don't know what they do. You don't know why is that there. Everybody is probably going to know what 3.14 is probably standing for, but some mysterious magical number like that, I have no idea. Right? So avoid. Sometimes we call those things anti-patterns, bad habits that you should not get into. Instead, define a constant or define a macro like this. Right? All right. Good. All right. What's another part of this program here? So these were the this is the documentation up here. These are the preprocessor directives. The main entry point is the next part of this program. The main function is necessary for any executable program. It provides the start. Well, actually, no, I'm going to say that it defines. It defines where a program begins. Right? Begins. There we go. Everything has to have a starting point. And if you've got a program that that has you start the program and then it terminates, well, it's got we call that the life cycle of the program. You have to have a starting point. Every executable starting point or executable program in C, its starting point is the main function, right? So that's where a program begins. You know, let me go ahead and if I do this. Oops, nope, that's not what I wanted. So, come on. Okay. Commands, or I guess executable statements inside the main function, there we go, it is still working, are executed sequentially. That is, top to bottom, in general, left to right. Right? Just like we read. Right? We want our programs to be legible, and so they design these things. They design programming languages to be read left to right, top to bottom. And I don't know of any other. I don't know of any other programming languages that kind of violate that. There's no such thing as a programming language that goes top to bottom or something like that. That would be very, very difficult for people to read because they're not used to that. Right? But that's the main. Right? There are other items, such as int, argc, int, or char, argv, star, argv, etc. We'll skip those details for now. Right? Don't worry about it. When you write a program, a lot of your first programs are going to be a lot of cut and paste. The preprocessor directives are going to be probably cut and paste. The main function is going to be cut and paste, and then you need to start writing your own program within that main function. When we get to more advanced concepts, for example, char star argv, that's a double pointer to a character array. Don't worry about that. It's just a two-dimensional. It's an array of strings or a two-dimensional character array or a matrix of characters. Again, don't worry about it. Int, however, is something that we are going to be looking at very shortly here. What do you think it's short for? Integer, exactly. Right? And so there are types. You have other. But before we get there, let's note our other syntax and punctuation. Right? For example, semicolons. And end executable statements. Right. Let me go ahead and go back up to the program here. That preprocessor directive, that was something for the preprocessor. It was not something that our program executes. Consequently, there is no semicolon after it. Main, opening bracket, opening curly bracket, closing curly bracket, those by themselves are not something that the program executes. It's just something to encapsulate a bunch of executable statements, a function, right? And we'll get to functions later on. But those don't have semicolons at the end of them. Everything else inside that function does, except for, of course, what doesn't have, inside that function, what does not have a semicolon at the end of it. Comments, because comments are ignored. They're not executable statements. But the declaration of variables, print, scanf, multiplication and assignment, and then another print and then a return, all of those have semicolons at the end. Generally, white space doesn't matter, but you should make white space a priority so that for readability. And we'll talk about style later on. Double quotes, mark or delimit strings, which are sequences of printable characters. Right? So again, we saw that up here with hello, the message "Hello World," right? Or sorry, not "Hello World," but this more substantial program here. Please enter miles. Right? Those were enclosed in double quotes. Single quotes are something different. All right, and we'll get to that later. All strings have to have double quotes. They have to begin with a double quote. They have to end with a double quote. Just like they do on this line, just like they do on this line, and just like they do on this line right here. Right? So anything that you want printed or anything that needs to be formatted, a string needs to have double quotes surrounding it. Commas delimit various elements. For example, variable names, function arguments, etc. And we already observed that, right? Up here when I declared miles and kilometers, I separated them with a comma. Down here when I printed them out, I separated the string and the miles and the KMS all with commas. All right? If you've got a list of things, just like in English, you delimit them with a comma. All right? Curly brackets delimit what are called code blocks, right? Which are blocks of code that are treated as one unit, right? One logical unit, I should say. The opening and closing curly bracket that I put for my main function, everything in that is part of the main function. This is the beginning of the main function, this is the end of the main function, and things are read sequentially within that main function. Right? And without those curly brackets, how would you know where a function begins and ends? Right? There are some other languages that use different strategies. Python was mentioned before. Python uses indentation to indicate the beginning and the end of a code block. There are definitely drawbacks to that. But the vast majority of languages, C-style syntax languages, will use opening and closing curly brackets to denote code blocks, including Java, C++, C#, anything that's basic, Objective-C, anything that is basically derived from C is going to be using that style of syntax. As I said before, in general, white space does not matter, right, to the program. That's the important part. I could go back and take out all the white space and put however many lines of code was that? How many lines of code was it? 1, 2, 3, 4, 5, 6. I could take all 6 of those lines of code and put them on one big, giant, long line. Right? Think that's readable? Probably not. The compiler doesn't care because the compiler goes and sees executable statement, semicolon, that's the end of it. Next executable statement, semicolon, that's the end of it. And in English, we do that, right? You don't put one sentence per line in your English paper. You put it all together in a paragraph. But with code, it's a little bit different. Each executable statement is one logical execution. So it's much better if you put one executable statement per line. Right? Generally, you don't want to put extraneous white space. You don't want to double space everything just so that you have a lot of white space to look at. But there's other aspects to white space here that don't matter to the compiler, but make this more readable. Right? What kind of white space? Where? Up at the top of the comments. So I've got I've got an author, date, and then I've got an empty line, and then the actual description of the program, right? What about the lists again with the commas? What did I put there? I could have put KMS or miles, comma, KMS without a space there, but would that look right? Probably not. The compiler wouldn't care, but we would care as humans. That doesn't look right. You wouldn't do that in English, right? What other white space do you see? Yeah. The indentation, right? Everything in that main function is one logical unit. It goes top to bottom. It's all indented, and it's all indented at the same level. I've indented using 2 spaces here. You could indent using tabs. You could indent using 3 spaces. You could indent using 4 spaces. 5 spaces is probably getting unreasonable. But the key here is to be consistent about it. If you are a two-space indentation person, then go ahead and go. Everything should be 2-space indentation. If you are a tab over indentation person, everything should be a tab over on the indentation. And everything in the same logical unit should be indented at the same level. Again, appealing to what you know in English papers. An outline. Right? If you've got an outline of a paper, Chapter 1, Chapter 2, Chapter 3, then within Chapter 1, you've got Section A, Section B, Section C. How is it formatted in that outline? Subparts are all indented, and they're all indented at the same level. Everything at the same level is indented at the same level over here in your outline. So follow those conventions. The minutia doesn't matter. Again, if you want to do tabs versus spaces, that's up to you, as long as you're being consistent about it. Right? So white space is important for style. Right? It makes a program more readable. More readable. Right? And finally, there are several reserved words. Right? Double, say printf, etc. Those are words that are defined by the language, just like English defines every single word that I've been saying up until this point. If I make up a word like I did before, like I mentioned before, grok, right? That's not English, right? It's entered our lexicon and it's become English slang. But there are certain words that are not English and have no. If you just make up a random word, right? Nobody's going to understand what you mean, right? So computer programming languages are the same. They have this much smaller set of reserved words that are defined by the language and that are understood by the compiler. If you go and start making up your own words, again, the compiler is not going to understand because it's not part of the language. Right? So we'll get to all of those keywords here in a moment. In fact, in our last 15 minutes here, let's talk about variables. C is what's called a statically typed language. Don't worry about the technical meaning of that. All it means for you is that every variable must be declared along with its name and type before it can be used. Right? What do we mean by declare? Declaration just simply means that we have a line of code that basically it's an executable line of code that defines the variable's type and its name. Right? Then the technical word for names are identifier, or identifier. Right? There we go. If you hear me say identifier, I just simply mean the name of the variable. Right? Don't get fancy. Don't get technical. Just call them variable names. Right? The identifier is the technical name. Statically typed, again, just simply means that you have to declare it before you can use it. If you don't declare it before you use it, the compiler is not going to know what you're talking about. Before in my previous program here, I declared that there were 2 variables called KMS and miles. That was the first line of code, in fact, in my main function. If I did not declare those, then later on when I try to read in miles and then use it in an expression to multiply by some other number, the compiler wouldn't know what the heck I was talking about. Miles, what's that? I have no idea what that is because you never declared it. And you'll get an appropriate error message from the compiler saying so, that it has no idea what you're talking about. Right? The second part of that is its type. So types of variables. There are several types of variables that are supported by C. I'm only going to focus on the three most important ones. Right? I'm going to focus on int. Oops, int. There we go. I'm going to double and char. There we go. So you already answered this question. What do you think int stands for? It stands for integer. Why the heck didn't they just call it integer then? Right? Well, think back 40, 50 years ago. Right? Computers measured memory in bytes and kilobytes. My hard drive here is maybe 500 gigabytes. Right? 500 gigabytes. There did not exist a computer 50 years ago that maybe all the computers combined in the world maybe approached a few gigabytes. When you measured a computer in terms of kilobytes, characters mattered. So if you could abbreviate something, then you did it because it saved a lot of space. Integer, I-N-T-E-G-E-R. Oh, I just saved 4 characters, right? And if I'm doing that 10 times in a program and 50 different programs, that's a huge savings 50 years ago. So that's why they still use these abbreviations today, because it was born out of C. It was born out of very limited memory 50 years ago. Likewise, char. It's short for character, right? And of course, you're even saving even more when you go from character down to just char. Double, it's the full word. Don't ask me why they didn't abbreviate that one either. But we'll get to each one of these here. This is an integer variable, which can represent a value, or a whole number of values from, and I'm going to have to cut and paste this. There we go, because I don't want to get it wrong. Or between. There we go. Negative 2, that's 2 billion, 2.147 billion, and then positive 2.147 billion. And the reason is, now there is a technicality here. The C standard actually says that that an integer has a minimum of 2 bytes, which actually represents only 32,000 negative and positive 32,000 negative values in that range. Don't worry about it. I've never seen a system outside embedded applications where that was the case. In 99% of the cases that you'll encounter, it's this range, about negative 2 billion up to positive 2 billion. And the reason that we can't express something larger or smaller than that is because an integer is only 4 bytes. What's a bit? A bit is 0 or 1. What is a byte? It's 8 bits. So if I've got 4 bytes, then I've got 4 times 8, 32 bits. I've got 32 bits with which to express a number. One of those bits is going to be used for the plus or the minus. 0 for plus, 1 for minus. The remaining 31 bits are going to be used to express the value of the number. Well, guess what? Let me go ahead and pull up a web browser here. And I might need to go small here. What do you think 2 to the 31st power minus 1 is? 2.147 billion. Exactly the number that I just gave you. Right? If you only have 31 bits to represent a number, that's the maximum value that you can represent. 2 to the 31st minus 1. Why minus 1? Because it starts at 0. Right? So you can't go all the way up to 2 to the 31st because you start your representation at 0. To go the other way, it's a little bit more complicated. It's what's called 2's complement. Don't worry about that in this course. If you're interested, go ahead and read a little bit about it in the book, and it shows how 2's complement, I believe I wrote how 2's complement kind of works. But you can kind of see this in the small. Forget about binary for a second. What if I only gave you, say, 3 digits to express a number? What's the maximum value that you could express? 999, right? That's the maximum value that you can express. What happens when you add 1 and get 1,000? Well, you don't have 3 digits. I didn't give you 3 digits. I didn't give you 4 digits. I only gave you 3 digits. So what ends up happening? It rolls back to 0. That's called overflow underflow. If you get too large of a number, if you get up to 2.147 billion and some change there, and you have that number right there, and then you add 1, you go up to 2,147,483,648. But guess what happens? It rolls back to the other side, giving you that negative value over there. Because it's a cycle. It's not a line like the number line. It is a cycle. You start out at 0 over here. You go positive, positive, positive. Over here, you can go negative, negative, negative. But they eventually come around and meet each other. And so if you go too large, you're going to come back to this. And that's called overflow and underflow. We'll take a look at that later on. Understand that you are limited to that range with an integer value. It's pretty standard. If you do have need to represent larger numbers, there's a long, which is a 64-bit number, but you still have the same problem. Eventually, you're going to have overflow. You have a long, which is a 128-bit number, but again, it's just finite. Computers are finite. You don't have an infinite number of bits to work with. So at some point, you reach your limit. If you do need to represent much, much larger numbers, you have to bring in what's called a multi-precision library. GMP, GNU's multi-precision library would be my go-to for that. And then basically the way that it works is instead of using the built-in integer types, if you're about to overflow and add too much, it allocates more memory to store that additional information. You pay a big price for it because it's all done in software rather than hardware. It's much, much slower. But if your application needs it, then you'd have to bring in a library. Right? Doubles are basically what are called floating point numbers, right? That provide 16 to 17 digits of accuracy. So 3.14159, you could represent that using a double. You would not be able to represent pi using an integer because integers are whole numbers. You could represent 3, you could represent 4, but you can't represent anything in between. If you need to represent fractional numbers, then you need to use a double. Again, it's going to be finite. In this particular case, a double is a 64-bit IEEE 754 number. Again, forget about that technical babble. The take-home point of this is that you only have 16 to 17 digits of accuracy. Now, if mathematics, if the Apocrypha is to be believed, that is more than enough to represent the size of the universe accurate down to 1 nanometer or something like that. In other words, for the vast majority of your applications, that much precision is probably going to be sufficient. You can have long doubles, doubles, which are going to offer more and more precision, or you can bring in a library to have an arbitrary precision if you really want to, and calculate pi out to 1 billion decimal points. We're not going to do that here in this course. Int and double. Whole numbers, fractional numbers, good enough for now. Right? A char is a single ASCII text character. Right? ASCII here refers to the, now I'm going to have to appeal to my web browser again. What is American Standard, yeah, character interchange, blah, 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 blah. The top, American, you can't probably read it, I'll read it to you. American Standard Code for Information Interchange. I believe that it goes all the way back to the 40s. That's why it's got the A in the name. It's American. So it's obviously going to be biased towards the English alphabet. And you can't see it really well. Let me go ahead and zoom in here. But there's the table. Right? There are a bunch of control characters here. For example, you can make your terminal beep with one of them. But when it gets up here to the actual useful characters, for example, space. Space has a value of 32. Right? There are 128 characters defined by the ASCII text table. If you want to look at the extended ASCII text table, then there are 256, in which you get things like U with an umlaut above it, or N with an enya above it, right? Those are in the extended ASCII character set. And you can use those in C if you want to. But these are the standards. Space, the exclamation point has a value of 32. What about A? Capital A. It has a value of 65. And lowercase a has a value of 97. And guess what? They're all in order. Right? There is a rhyme and reason to this. There are lots of little tricks that you can do to convert from a capital to a lowercase. Uppercase come before lowercase. It's all called lexicographic ordering. Numbers come before letters, and certain punctuation, like for example, those are only 2 away. Those are 2 away as well. It looks kind of like an animation here, right? It's going back and forth or something. But you've got all these you've got all these characters that are defined by the ASCII character set. Again, there are 128 common characters. Of course, English and letters and punctuation, right? That each have a numerical representation. Again, capital A, what was it equal to? 65. It has a value of 65. Good. All right. Why do I mention that? Because what is a computer? A computer is just a bunch of zeros and ones. There's not really a letter stored in a computer. There is a numerical representation that we associate with that letter that's being stored in the computer. Bunch of zeros and ones, it's all just numbers. At the end of the day, everything stored in a computer, memory, program, whatever, it's all just data. It's all just a bunch of zeros and ones. It's nothing more than a bunch of numbers. So to get representations like A, B, C, we need to set up a scheme by which a number is associated with that thing. This is ASCII. And the last few minutes here, let's do something fun. This is ASCII. Well, that's great for English characters. What about for international characters? Cyrillic, Japanese, Chinese, Korean, all that stuff. That comes much later in the history of computing. That comes in with Unicode. Right? Unicode characters, as an entire Unicode consortium. I don't know, example. Yeah, they're representations of not just 1 byte, but 2 bytes, 3 bytes, or 4 bytes to represent a single character. So that now you don't have just 128 characters. You have several million possibilities. And not all of them have been taken, but the Unicode consortium there is responsible for associating a number with a character that you want to produce. And of course, the international fonts, CJK, that's Chinese, Japanese, Korean fonts, they've been there for many, many years. What is more recent, though, is something that you might be familiar with. Unicode Emojis. Oh, I didn't spell it right, but let's see. So let's look up one. I don't know how to type them. So emoji, happy face with sunglasses. There we go. All right. There we go. Smiling. Now I'm going to look up there. It's Unicode value. Emojipedia. All right. Is it going to actually tell me? No. Oh, there it is. Right there. So there's its Unicode value. If you can see that. 1F60E. Right? It has a number associated with it. And all the emojis that have been created in the last 5, 10 years, whatever, however old they are, they're nothing more than numbers. Numbers that get interpreted in different ways on different systems, just like fonts get interpreted in different ways in different systems. But They're all, every F that you see on a computer is the same F because at the end of the day, it's the same number. Yeah, question? Oh, so